Hello, today we'll see the fourth part on negative refractive index. Yesterday we saw why materials which has double negative characteristics are called left-handed materials. Today we'll see that if materials have double negative characteristics, then the group velocity and phase velocity are of opposite sign. That will. So at the end of discussion yesterday, we saw some of the objections to double negative material, to the existence of double negative material. Today, we'll see the replies, what replies are given, and gradually we'll see one by one the replies or the justification for the replies. What are the replies? The first reply is the momentum conservation is not violated. It is not the parallel momentum which is not being conserved. Total momentum is to be conserved. Either parallel momentum or perpendicular momentum of k vector, that is not under consideration. Total momentum is under consideration. Next reply was the causality is also not violated. That we will just now see how causality is not violated. Next. And then we'll see mathematics and physics behind the negative index. So we'll prove that the index is negative. Then we'll see that Fermat's principle is okay because integration of NDL is an extremum, it is not minimum. So if you consider it to be minimum, then Fermat's principle is violated, but considering it to be extremum, it is okay. And finally, we'll also see superlensing is possible. That also we'll see with one example. Under certain limitations, superlensing is possible. So these are the four replies to the objections that were raised and which we discussed in the last discussion. Next. Now let us look at the causality. To look at the causality condition, we will consider the energy density in a medium which is showing double negative characteristics, which means mu is negative and epsilon is negative in the medium. Let us start with time average density of energy in that medium. So we will find out energy density, time average energy density in that medium. Assume that first we assume that there is a non-dispersive medium. Usually mediums are non-dispersive, so we will consider a non-dispersive medium. In the non-dispersive medium, the energy density U, ND stands for non-dispersive here, energy density U. The formula is 1 by 4 epsilon absolute E square plus mu absolute H square. Now epsilon and mu both are negative, therefore energy density is negative, which means that energy is being created out of nowhere. But energy cannot be created out of nowhere because of the conservation law of energy. So energy conservation is being violated. This violates the causality condition because without any cause there is high energy generation. This was the objection for mu and epsilon negative in the non-dispersive medium. The energy density will be negative. This is a non-physical result definitely because of this. Now look at this expression for energy density. The generalized expression for energy density is U is equal to 1 by 4 as it is, but for epsilon we have partial derivative with respect to omega of omega epsilon. If epsilon is constant, then this partial derivative gives you epsilon, but if epsilon is a function of omega, then it is not epsilon, so it will be different. That into E square. Similarly, for mu, we have to take the partial derivative with respect to omega of omega mu. Now remember that we have said that epsilon and mu both are dispersive in the DNG media. Therefore, both are functions of frequency. Accordingly, both are functions of omega or angular frequency. So, this is the actual uh, uh, expression for energy density in the DNG media or in the regular non-dispersive media. This is the actual or the generalized formula. Next. Now, this has to be true provided u is positive. Now, for u to be positive, both these partial derivatives must be greater than 0. So the range in which both these partial derivatives are greater than 0 and epsilon is negative, mu is negative, over that range we say the media is DNG media, and there we are experiencing DNG phenomena. And double negative phenomenon, left-handed phenomenon we are observing there. So the physical media has to be dispersive for DNG double negative media. The media has to be dispersive in nature. If it is non-dispersive, then we cannot have DNG media. It has to be dispersive media. So remember from this what we conclude is the derivative has to be positive because energy must be positive. Therefore, if a derivative is positive, then the LHS here, in any case, will have dispersion and it will have a KKR absorption. KKR is Kramer-Kronig relationship. So in physics, we are acquainted with Kramer-Kronig relationship. Let us see that Kramer-Kronig relationship for the refractive index. The Kramer-Kronig relationship for the refractive index are given here. The real part of refractive index and the imaginary part of refractive index under Kramer-Kronig relationship are expressed by these two expressions. Next. So in this expression, there is a theorem which is called the Titchmarsh theorem. The Titchmarsh theorem says that if Kramer-Kronig relationship is satisfied, then causality is also satisfied. If causality is satisfied in a medium, then the medium must satisfy the Kramer-Kronig relationship. Since Kramer-Kronig relationship is being satisfied, then by virtue of Titchmarsh theorem, causality is satisfied for the DNG medium. Now let us look at the group velocity. So causality we have seen. Now let us look at the group velocity. For group velocity, the definition is it is the ratio of the magnitude of Poynting vector to the energy density. So Vg is equal to S by E. The magnitude of Poynting vector S is equal to minus root over of epsilon by mu E dot E into K upon K absolute. This is the Poynting vector. Similarly, energy density we have just seen 1 by 4 into this expression, the expression within the bracket. So if you take the ratio 1 by 4, it is in the denominator, so that goes to the numerator. S has minus, so minus has come there, so minus 4. Then root epsilon by mu, that comes from S. E dot E comes from S. K by absolute K, that comes from S. Rest of the factor is coming from U. It is inverted because U is the factor, so its inverse will be in the numerator. So this is the group velocity, expression for group velocity. Now let us try to simplify this expression. If we simplify this expression, what we will do is E dot E actually is E square. So let us take that absolute E square. So if we take absolute E square inside the bracket, and then what we'll get? Absolute E square, let us take that into the bracket. Into the bracket, if we take the absolute E square, so the first term will be absolute E square. then absolute T square inverse. The first term is absolute T square inverse, so that will cancel out. Second will be absolute T square, then absolute H square inverse. So E by H as square. E by H we know is epsilon by mu. So put that, then Vg is equal to minus 4 root over of epsilon by mu into 1 upon and dou by dou omega of omega epsilon plus epsilon by mu dou by dou omega of omega mu. That into k upon k absolute. So this is the group velocity. Now if you look at this, the group velocity is negative here. Group velocity is negative means it is in the negative direction of k. So k is in the negative direction of s or the pointing vector. Group velocity is in negative direction of k. So group velocity is in the direction of the pointing vector. So pointing vector and group velocity, they are in one direction. K is in the opposite direction to group velocity. Now that we can conclude from this, the denominator is positive, group velocity is parallel to pointing vector and anti-parallel to the wave vector. So on this gives us negative group velocity. So with that, we will stop for today's discussion. The next discussion will be, oh, this is that. And now let us see what happens because of this. Now find out dou k square by dou omega. Dou k square by dou omega, that we can write as dou k square by dou k into dou k by dou omega. Dou k square by dou k is 2k. So 2k into dou k by dou omega, that we can write as 2 into dou k by dou omega is actually k into dou k by dou omega, that is actually omega by Vp into Vg, because k is equal to omega into root over of epsilon mu. So using that we get k into dou by dou omega of k is equal to 2 omega by Vp into Vg. Next. So then also we know on dou k square by dou omega, this is also omega epsilon into dou by dou omega of omega mu plus omega mu into dou by and dou omega of omega epsilon. This we get from k square, because k square is omega square mu into epsilon. So by partial derivative, then we get this expression. First you take the derivative with respect to mu, then with respect to epsilon. So accordingly we get this equation. Now this, since the partials are greater than 0, so on this will be always less than 0. Partials are greater than 0. Epsilon is negative, mu is negative, omega is positive, therefore dou k square by dou omega will be negative. Now compare these two equations. If you compare these two equations, dou k square by dou omega is negative, which is equal to 2 omega by Vp into Vg. So 2 omega by Vp into Vg is negative. 2 is positive, omega is positive, which means Vp into Vg is negative. So product of the phase velocity and group velocity is negative. So backward propagation is implied by the negative sign between phase and group velocity here. Yes. So what does this physically mean? Physically it means that wave packets and wave fronts, they are traveling in opposite directions. And this is an additional proof of backward wave propagation. Phase velocity and group velocity are antiparallel. That you can see a simulation of phase velocity and group velocity. We can see we have taken a slab, DNG slab. So this is the white rectangle border. Within that material is the DNG material. We can see the propagation within that material. Outside that material, the propagation is towards the material. But inside the material, you can see the energy is propagating out of the material from left to right, whereas the group velocity, phase velocity is propagating from right to left on the left hand side. On the right hand side, you can see how the refraction occurs. Refraction is occurring here from the incident is from the third quadrant. At the interface, it is going getting refracted to the sorry incident is in the third quadrant. It is refracted towards the fourth quadrant. Then when it is coming out of it, again it is going to the third quadrant. So this is because of the DNG behavior. With that, actually, we come to the end of today's discussion. Next time, we'll discuss other things of DNG material.